This video demonstrates how to conduct a one-sample test of a hypothesis about a population mean when the population standard deviation is known. An airport manager has to decide whether to expand the space available for short-term parking at a small regional airport. If average parking time is more than 40 minutes, he can justify expanding the lot. Several years of data indicate the parking time has a standard deviation of 10 minutes. Lately, customers have complained that it is difficult to find space in the lot, and the manager believes the parking time has increased. He has randomly selected a sample of 12 cars' parking time, shown in this file. Excel doesn't have a hypothesis test specific to a one-sample test of the mean, but we are going to adapt the two-sample z-test to our needs. First, I'll set up a dummy variable in column B, and I've entered a 0 so that there is a value in this column. Then I'll go to Data, Data Analysis, and I'll go all the way down to the z-test, two-sample for means. My variable 1 range is the sample data. I'm going to include the column header. My variable 2 range is the dummy and the 0. Let's consider what our null and alternative hypotheses are. The null hypothesis is that parking time is less than or equal to 40 minutes. The alternative hypothesis is that parking time is greater than 40 minutes. Therefore, the hypothesized mean difference is 40 minutes, what the mean is that we are testing. Variable 1's variance, notice that it says known. Because we're using a z-test here, we know the population standard deviation. For variable 1, we are going to enter the variance for the population, 100. Remember that we are adapting a two-sample test to a one-sample test. We don't have a second variable's variance, but we cannot enter a 0 because Excel will not allow that. So we're going to enter a value as close to 0 as we can so that it won't affect our final results. I click to select Labels. My alpha is 0.05. I'll have my output in this tab, and now I'm ready to click OK. I'll expand the results so we can see everything. You can see this dummy column here. We don't need this column. We're also able to change this from a z-test for two sample to one sample. And here it's the hypothesized mean, not the hypothesized mean difference. Now we have our output for a one sample test. The mean of our sample is 48 minutes. The known variance of 100, Excel has taken the square root of that and divided it by the square root of 12 in order to determine standard error, which was then used to calculate the z. If we take 48 minus 40 divided by 10 over the square root of 12, we get the 2.77. This is how Excel has calculated the test statistic. We're using a one-tailed test because we are testing the alternative hypothesis that mu is greater than 40 minutes. Our p-value is quite a bit smaller than our alpha of 0.05. When p-value is less than alpha, we reject the null hypothesis. This is the z-value that you would look up in the standard normal table based on a significance level of 5%. And compare it with the test statistic of 2.77. If the test statistic is greater than the z critical value, again, we would reject the null hypothesis. Either way, whether we use the p-value or the z-score, we would reject the null hypothesis. This video demonstrated how to use Excel's data analysis two-sample z-test to conduct a one-sample z-test when population standard deviation is known. This video demonstrates how to conduct a one-sample t-test of a hypothesis about a population mean when the population standard deviation is unknown. An airport manager has to decide whether to expand the space available for short-term parking at a small regional airport. If average parking time is more than 40 minutes, he can justify expanding the lot. Assume population standard deviation is unknown. He has randomly selected a sample of 12 cars parking time, shown in this file. Excel doesn't have a hypothesis test specific to a one-sample t-test of the mean, but we are going to adapt a two-sample t-test to our needs. First, I'll set up a dummy variable in column B and enter at least 2 zeros. Then I'll go to Data, Data Analysis, and t-test two-sample assuming unequal variances. In my variable 1 range, I enter the minutes, and I'm including the column header. Variable 2 range is the dummy column header and the 2 zeros. Our null hypothesis is mean parking time is less than or equal to 40 minutes. Our alternative hypothesis is that mean is greater than 40 minutes. Therefore, the hypothesized mean difference is 40. We check labels since we included column header, and we're testing at an alpha of 5% or 0.05. I'll put the output in this tab and then we'll click OK. I don't need the dummy column. I can delete that, and we'll change this to a t-test for one sample, and we can get rid of the rest of it. And this is hypothesized mean. The t-test statistic is equal to the mean of the sample minus the mean of the population divided by standard error. We get the same result when we calculate it by hand as when we have Excel calculate it for us. The probability of obtaining a sample mean as extreme or more extreme than this, if the population's mean is actually 40, is 0.008 or 0.8%. That p-value is smaller than our alpha of 0.05. When the p-value is smaller than alpha, we reject the null hypothesis, and we say that parking time is greater than 40 minutes. We can also compare our t-critical value, 1.796, with the t-test statistic, and because the test statistic is larger than the t-critical value, we would reject the null hypothesis. Either way, whether we're looking at p-value or the t-critical value versus the test statistic, we would reject the null hypothesis. This video demonstrated how to use Excel's data analysis two-sample t-test, assuming unequal variances, to conduct a one-sample t-test when population standard deviation is unknown. This video demonstrates how to calculate beta and power given the results of a sample from the population when population standard deviation is known. In this example, an airport manager has selected a sample of the time 12 customers' cars spent in the short-term parking lot. The population mean is believed to be 40 minutes, with the population standard deviation assumed to be 10 minutes. The manager will need to expand the parking lot if the mean time to park is longer than 40 minutes. That means we would conduct a one-tail hypothesis test. In the sample, the mean time is 48 minutes. The standard error of the mean needs to be computed to determine the x critical value, which will be used in calculating beta. Standard error is the population standard deviation divided by the square root of sample size. In this case, our standard error of the mean is 2.8868. Our alpha, or the allowable probability of making a type 1 error and incorrectly rejecting the null hypothesis, is 5% or 0.05. To compute beta, we first need to compute the critical value in terms of minutes. Equals norm.inv, and for probability it's going to be 1 minus the alpha, because this is a cumulative probability formula, and we want to know what is the x that corresponds to the z and our upper tail, which means 95% of the curve is to the left of that. Next, the population mean, and then the standard error as the standard deviation of the sampling distribution. Then we can close the parenthesis and hit enter, and our x bar, or the x value that corresponds to the z critical value is 44.748 minutes. Now that we have the critical value in minutes, we can compute beta. Beta is the probability that we will fail to reject the null hypothesis even though it is false. Consult your statistics textbook for an in-depth discussion of beta. To calculate beta, we use equals norm.dist. The x value is the x critical value that we have just calculated. Our mean is the sample mean. Then we use the standard error as our standard deviation. Select cumulative because we want the cumulative distribution function. The beta is 0.13 or 13%. There is a 13% probability we would fail to reject a null hypothesis that is actually false. Power is just 1 minus beta. Power is the probability that the test will detect a difference between the sample and the population when there is actually a difference. This video demonstrated how to calculate beta and power for a one-sample test of the mean when population standard deviation is known.